Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to talk calculus, getting it straight, differentiability as local linearity. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to be joined by our two panelists tonight, Tom Dick and Dan Kennedy. Tom is a professor and former chair of the math department of Oregon State University. He has served on the editorial panels for the Journal for Research in Mathematics Education and the Mathematics Teacher Educator. He remains active in the College Board's Advanced Placement Calculus program and has previously served as chair of the AP Calculus Test Development Committee. Tom, so great to have you with us tonight.
It's great to be here, Mike. Thanks.
And Dan began teaching over 30 years ago in West Africa. For the past 20 years, he's taught all levels of math and various sciences to a diverse population of students in Tucson, Arizona. In addition to his classroom responsibilities of physics and AP calculus, his school and district have given him the added responsibility of acting as a teacher technology liaison. So Dan, we're excited to have you with us tonight.
Thanks, Mike, and thanks, Tom, for having me.
We're expecting a large crowd, so your audio is automatically muted. Feel free at any time to send any questions to Tom or Dan using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance, as well as a link for the documents being used tonight at the conclusion of the webinar. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the WebEx menu and choose Audio Broadcast. At this point, Tom is going to discuss our agenda.
Okay, thanks, Mike. Well, we've done the introductions, but in just a bit, Dan's going to discuss our learning outcomes. But the big idea we're going to be looking at is this idea of local linearity. We're going to touch a bit on the work of David Tall. He's a math ed researcher who had really some interesting stuff to say about this concept, which is really fundamental to differential calculus. And we'll illustrate a way you can understand L'Hopital's rule through this notion of local linearity. And then we're going to take a look at some calculus problems and really see how the local linearity plays out in looking at difference quotients, approximating derivatives from a table of values. And then we'll actually kind of shoot forward in the course because it relates back to this idea of local linearity is the notion of slope fields when you're looking at antiderivatives and other differential equation solutions. It's really local linearity that's behind that really nice graphic application. So I'll turn it over to Dan now.
Yeah, and Dan is going to discuss some of our expected outcomes.
Okay, and they are, we're going to explore the differentiability in terms of local linearity and discuss when the tangent line really is the best linear approximation. Explore why L'Hopital's rule makes sense through local linearity, because otherwise students might think of it as just a black magic trick sometimes. Analyze some applications of approximating derivatives, and examine how slope fields make use, as Tom had mentioned, of that local linearity.
Dan, thanks so much. Tom, you should have control. Feel free to share your screen. It's all yours.
Okay. Let's see. I'll share my screen. And actually, Mike, was there one more slide after that we should talk about? Or
there was, actually. If you want to stop sharing for a second.
Okay, all right. Oh, sorry for that little fumble there.
And then if you just advance that slide on the left side, there's a 7 on the left side of your screen, Tom. You can actually advance it to slide 8. I don't know if you see the slide changer on the left side of your screen there. There's little up and down arrows.
On the left side, okay. Well, I'm looking at the left side, don't see it.
Okay, let me,
okay, wait a second.
I already took control back. Sorry. Let me.
Okay.
I think that's what you're looking for.
Yes. Okay. Thank you. So this local linearity, just wanted to say a few words about what exactly that's referring to. And it's this property that of differentiable functions is that they have this property that if you zoom in, look at their graphs up close, their graphs look more and more straight. And that's kind of a simple notion, but it turns out to be really profound. That really captures what differentiability means. It's functions that on a local level behave like linear functions. And if your students are like mine, those are some of their favorite functions to work with, are linear functions. And differentiable functions on that small scale behave that way. That's something I didn't really come across as a way to think about differentiability until I'd actually been teaching calculus for more than a few years. And I think the thing that really brought it home to me was how well it manifests itself on a graphing calculator. The fact that you can zoom in dynamically on a function graph really lets you exploit that idea of local linearity in a way that it's hard to do with paper and pencil. And I think that doesn't mean we don't still talk about secant lines approaching tangent lines, but I think the fact that you can just zoom in directly on a differentiable function graph and appreciate that is really powerful. I gave mention to this math education researcher named David Tall. He's a real giant in the field. He referred to this local linearity property as a cognitive root for differentiability. And what he meant by that was it was really, you could really hang your hat on it. It was an anchoring concept that could really guide your intuition. All right, so why don't we go ahead and illustrate that? So let's see. So Mike has given the ball back over to me. I'll go ahead and share my screen. And I'm going to illustrate this first of all, I think, with just the TI-84. Okay, so I've got the TI Smart View up so we can take a look. And I'm just going to go to the Y equals menu and enter simple function. Let's look at sine x. Okay. So there we go. And I'm going to use a window. The window I prefer on the 84 for a lot of, especially when I'm thinking about slope, is the zoom decimal window. And the zoom decimal window, I think of it as like 1 pixel per is worth exactly 0.1 in both directions. So you can kind of judge what slopes are, and it's got a nice regularity to it. So if I was to trace on this, the increments are going to be 0.1 in the x direction as I trace along that function graph. Okay? Now I've gone back to the origin, and all I'm going to do now is simply zoom in on the graph of the sine x function. So let me go to zoom, and we'll go down to zoom in. And once you've entered zoom in, okay, it's wanting you to center the screen where you'd like to zoom in at, and we're going to keep it right here at the origin. So I'll hit enter again. And we see the graph. It's close-up view. We still see the curvature of the sine graph there. And if I hit enter one more time here, it's just going to repeatedly zoom in again and again at that point. And with just a couple of zooms, this graph is really straightened out. And in fact, if I zoom in a couple of more times, I see that the graph looks perfectly straight. In fact, it looks indistinguishable from the line y equal x. And I was doing a workshop once where somebody kind of stumbled on this, and they said, oh, my graph looks straight. And they said, wow, that's profound, isn't it? And it really is. That's what local linearity is really about. In fact, if we were to trace on this graph, we're actually going to be able to detect that it's not quite straight. But look at that. The x increment here is this number 3.906. But look, the y incremented not quite exactly the same amount. So we can see we really are on the curve y equals sine x, but it looks very much like the line y equal x. And that's a very powerful idea. that near 0, sine x behaves like y equal x. So let's do another example and get a sense of this local linearity at another point on a different function. And I'd like to make talk a little bit about this idea about best local approximation. So I'm going to go to my y equals menu, and I'll just clear out the sine x. And I'm going to go ahead and put in a function maybe all of us have used as one of our very first examples of a nonlinear function to investigate in calculus, and that's just y equal x squared. So I'm going to enter that. And again, let me just go to my zoom decimal window, get our regular window up again. And there's our nice parabola. And I'm going to trace over to this point 1, 1. We can see with this curve, so I'm curious about kind of checking out what's the slope of the curve locally at that point. So the idea of derivative there. And now I'm just going to do that via zooming. So I'm going to zoom in. And here we go. So we can see it's still a parabola. Well, it always is still a parabola, but as we zoom in, it looks more and more straight. And now I've zoomed in maybe overkill, but I've zoomed in several times, and it looks like a straight line. Now let me just look at the trace and see if we could think about what's the slope of this line. So my trace increment, well, we can see it right here. I traced just one pixel, and it was 0.00000061. And if I look over at how much y got incremented, notice it got incremented by exactly twice that much. I shouldn't really say exactly because we only see these truncated or rounded off to this many decimal places, but it's approximately very close to twice as much of an increment in y per that increment in x. Let me go another increment in x. I'm still seeing that kind of 2-to-1 ratio of y increment to x increment. And notice I'm really talking in terms of the language of a line. You know, what's the rise over run that I'm seeing on what looks like a line? And I'm reminded up here on the left that I'm really looking at a very close-up view of a parabola, but I can appreciate that I've got this locally linear approximation to it just by zooming in. In fact, some people have fallen into this trap of, and it's actually a nice trap to fall into. I'm going to go back to the y equals menu and say, well, what if we looked at both the tangent line and the graph and zoomed in on those? So I'm going to, let's see, we had a slope of 2 at y equals 1. So if I figure out, I think my tangent line would have to be y equals 2x minus 1. So we have the right slope, and then I'll go through 1, 1. So I just kind of did my point slope form in my head there. And so now I have both the y equals x squared and a function representing its tangent line at x equal 1. So let's do our zoom decimal. So there we've got the nice parabola and the tangent line. Parabola in blue, tangent line in red. And I'm again going to trace over to 1, 1 and start zooming in. Okay. All right, there we go. And notice the effect here is after a while you don't even see the original parabola anymore. Actually, you see it momentarily. If I press enter, you're going to see a blue graph come up, but then the red graph is just right on top of it. And if we were to trace on this, okay, now this tells me I'm tracing on the parabola, y equals x squared. If I was to switch over to the tangent line, notice at this scale, those values are exactly the same. If I continue to trace out a little bit further and switch over to the other function, now I'm detecting a little bit of a difference here that we can't see on the screen, but we can detect with how fine a decimal approximation we have here on these values. So that's really the idea of local linearity. And it's a very simple, very powerful, and graphing calculators just give us a tremendously nice way to think about that. And what I really like about it is that difference quotient idea of the limit of difference quotient definition of derivative that in my early teaching, I think my students' view was that with some torture I was putting them through trying to do these derivatives by definition, and then we would get to the shortcuts. But with local linearity, this difference quotient idea makes perfect sense. It's, of course, okay, well, up close, that's the idea of the limit, is the closer we look, the more linear it looks. And so the limit of the difference quotient is just a slope calculation that we're doing on this apparent straight line. Now let me turn, I'm going to switch platforms on you a bit here. I'm going to switch over to the TI-Nspire. And I hope you're able to see that. And I'm going to talk a little bit about a tale of two lines. Okay, so it's kind of a cute name for this file. And what I'm going to show you here is a couple of graphs that both intersect the x-axis at the same point, x equal a. And what I'd like you to think about when you see these graphs is to think about the ratio of their y-values at any other point besides that common x-intercept. And we'll also look at the ratio of the slopes of these two lines. Okay, so let's go to that page and see what we're looking at. Okay, so I see a couple of lines, a green one and a red one, and they both cross the x-axis at the same point. Now let me go ahead and tell you that I haven't played any funny business on you here in terms of scaling in the following sense. The scaling is the same in both the x and y direction. So 1 unit in the x direction is the same as 1 unit in the y direction. So you can kind of trust your eyes as far as the slopes go. But let's just look at the y values at some point other than this crossing point. So for example, over here, let's say it looks like the green line is 2 units above the x-axis. And the red line is, let's see, excuse me, let me take that back. It's over here, it's 2 units above. Here it was only 1.5. So over here we've got 2 units above, +2. Down here we've got a -4. So the ratio of the y value on the green line is 2 to -4 on the red line. And over here, the ratio is a +1 to a -2, same ratio. And over here, now it's -1 to +2. And so at any point other than that common x-intercept, the ratio of the y value on the green line to the red line is in that ratio of -1/2. Now, if we were to compare the slopes of these two lines, notice that the slope of my green line looks like, here's a run of 2, down 1. -1/2 is the slope of the green line, and +1 is the slope of the red line. And again, the ratio of the slopes of these two lines turns out to be the same as that ratio of the y values that we saw. Now, the punchline here is, and I think it gave it away when I was sometimes near one of those lines, you actually saw what the actual underlying equation was. These weren't really lines at all. These were the graphs of 2 differentiable functions, and I was just looking at them up close. So we can see as we zoom out that what we were looking at was very close-up version of what's going on at this common x-intercept. And what we're seeing is up close, if your 2 functions have a common 0 and they're differentiable, that the limiting value of the slopes of the 2 lines will be the same as the limiting values of the function values. And that's L'Hopital's rule. And so this is just a really neat way to think about L'Hopital's rule. In fact, I was presenting this at a conference once where I didn't realize that the president of the Math Association of America was in the audience, and he came up to me afterwards and said, wow, I'll never think of L'Hopital's rule the same way again after seeing it via this zooming. So this local linearity idea, it is very powerful, very simple. but it really gets at the hard to differentiable calculus. Well, I think at this point what I'm going to do is I'm going to pass the ball over to Dan and let him share some stuff with you. So I'm going to stop sharing there and see if I can pull off this switch here. And there we go. So Dan, it's all yours.
Okay. Thank you, Tom. That was nifty. I'm looking forward to sharing that later in the year with my students when we come back to L'Hopital's rule. As a funny little side note, I do encourage, I'm sharing my screen, I do encourage my students to, pardon me, I'm going to flash back here real fast, to use technology in a lot of different ways. And we recently had a test that had to do earlier in the year with limits, and it was something like the sine of 3 over 2x all over 1 over x as x went to infinity, not to 0. And I let them work on it after the fact with corrections. And it was funny because, of course, they found a nice little limit calculator online, and they were using L'Hopital's rule, and they didn't even know what it was. They were already using it, and that was great. But I told them, you know, we'll get to that, but I did expect you to use your non-power tools at this point in the game. Okay, one of the things that I am very big on in using the TI technology is also trying to help the students with the assessment. And when Tom and I first started talking about this, he mentioned this specific free response question from last year's AP Calculus exam. I don't remember which form it is offhand, but anyway, you can find this. And though this is a non-calculator question, we're going to use the calculator to hopefully deepen the students' understanding of what's going on before they go into the exam of something like this. So if we're lucky this year, we'll get another problem like this, or maybe next year. And it's this idea of a local linearity. They tell you that you have a function. The tree is height. It's twice differentiable. It's important to know that. H is measured in meters. T is measured in years. I appreciate meters and at least as a physics teacher as well, because I always have problems with the feet. Selected values are up here. And then use the data. Okay, we're obviously not going to be doing the hand calculation here. I'm going to switch over real quickly to the data and rather the listen spreadsheets page that I made, entering all of this. And as I say at some of my presentations, this is kind of like watching, I don't know, maybe HGTV or a cooking program. I already did this up for you, but it's already sitting there. We're not going to spend time entering the data. But I love the fact that not using a data and statistics page, on the next page, you have a scatter plot of the data. And they wanted us to find, and pardon me for skipping back here, but going back to the wording, use the data to estimate, and that's the key here. We're estimating the derivative at the point of t is equal to 6 at 6 years. So we're going to use that local linearity concept and actually going to graph the line, and we're using essentially it's a metric difference here and not the actual definition of the derivative, but that's okay. Right, Tom? That's okay?
Well, it's the best we can do with the data that's given. We're just given
Yeah.
a few points here, so we'll use the two that are closest to t equals 6.
Yep. So I'm going to come in here and I'm going to go ahead and graph a line and point on, escape, and then right click, and I can go ahead and get the equation of my line. And there I have my value for the estimate of the derivative is 2.5. And if you go and look at the scoring guideline is also on here, and they show the wonderful calculation, and they got 5 halves or 2.5. okay? So there's our local linearity concept applied to a specific question from an AP exam. The next one isn't so much a local linearity, but since we were here, I really wanted to take the opportunity to hit on the second part to that question, which was to explain why there must be at least one time in the interval from 2 to 10 such that the derivative is equal to 2. So in that case, we're going to be looking at an application of the mean value theorem. And so let's see, I think I put that on the next page. Yes, I did. And I've gone ahead and put in the line y equals 2x and expect the students to be able to grab that line and play with it. And actually what I do when I do this in class is I come in and I'll draw a couple of different curves that could perhaps go through some of these points. But we can see that as we slide that over, it hits exactly on these 2 points from 3 to 5. So we know somewhere between 2 and 10 that there must be a point where the value, going back to the question, why you must have at least one. You know, we don't know. There could be more than one, but we know that we have to have at least one. Okay, so that brings us to the next component. Is actually our last, and I don't know, time is going by so slowly here. Normally these things go by so fast, but it's going by slowly. So I went ahead here and I looked at the slope field for y dx is equal to 1 over x, and actually gave it an initial condition of 0, 1, and put that in there. Now, I think most people suspect what that is. I'm going to go ahead and, I'm going to add in the actual function. And we see that, okay, if we have that initial condition of 1, 0, then we're looking at a slope field that matches the natural log of x. Okay, now we're going to look at a slightly different slope field. And of course, all of these wonderful. Yeah.
Is it okay if I interject here just a little bit?
Absolutely.
Okay. All right. Well, so I just wanted to just make the point that the slope field really is just taking advantage of the most rudimentary information we have, and that's that differential equation. If we know what x is, we know what the slope is of the curve. But the thing is, we don't know where the curve is. And so what the slope field is we've just picked a bunch of points, and at each point we said, well, if our curve went through this point, that would be the slope would be given by 1 over x for the x value at our point. And so it's just say, okay, let's just draw a little piece of what the graph would look like. And because we know it's locally linear, it'll be just a little line segment. So it's giving us a whole bunch of little tiny pieces of graphs. And then when we stand back from it, we can kind of see, oh, here's a curve that would follow that flow of the slope field. So sorry for the interruption, Dan. Back to you.
No, thank you. No, I appreciate it. It's the old stretch thing. I appreciate that. And going to the next slope field, we're looking at this one, and I've already put in e to the x. And we can see that it's kind of giving something away here. I shouldn't have put in the line y equals x right now. I apologize, but we're going to give something away here. And so we have a slope field for e to the x, and I've written over to the side here. One of these is actually related to what the differential equation is, and that was dy dx is equal to y. But in fact, let's go in here and menu, graph entry, edit, differential equation, up arrow. So there's our differential equation. And for those of you who haven't done the slope fields before on the TI-Nspire, and the students need to be have this pointed out as well. It's very important. Oops, escape. The other thing I love about the Nspire is I can just do my control escape. There we go. It is very important that you include that 1 right after y. And don't make the mistake of thinking, oh, you're going to put in dy dx is equal to y, because it needs that y1 because you're talking about y1. Okay, so I think that is very important because students will do it and they'll go, wait a minute, I don't have anything. There's nothing there. And then this part is just a text field, but it's trying to show the students that we've essentially taken the reciprocal of both sides here, and we have dx dy is 1 over y. Now, I'm going to jump out of the TI-Nspire software just so I can show you a little overlay here. And here is our natural log function, and here is our e to the x function. But here's the overlay. Now, it's a little bit busy. Apologize for that. But Tom and I were talking earlier, and this is something as an opportunity to show students, because invariably I've seen it, I think, almost every year the past 6 or 7 years on the AP exam, either in a multiple choice or somewhere in a free response, they're going to bring up this issue of knowing the derivative of the inverse function, just the value, not actually finding it and putting it in general form as a function. It would be impossible in most instances, certainly with the time involved, but you could find easily a numeric value at a point. The problem students run into is they choose the wrong point often. So let's take, well, we have our line y equals x here, and we have these nice slope fields that are, make these x's, okay, and they are reflections right across the line y equals x. But we got to be careful at these other points and not think that these are reciprocal slopes to one another. Where we really want to look, and one of the points Tom and I were talking about that maybe makes that a little more clear, is let's take the point it's fairly close to 2, 1, right about in here, and look at this little local linearity here from the slope field, and we're going to relate that to 0.12 over here, okay? And it's fairly clear, I hope, to the students. I talk a lot, starting even in Algebra 2, about this idea of inverse functions, that we have here those, I kind of refer to them as sister points sometimes. 2, 1 sister point is 1, 2. And it's those two derivatives that you can say are reciprocals to one another. And you can really drive the point home if you pick something, like if you were to try to say that these clearly are not reciprocals of one another. This might be fairly small. Maybe it's you know, a third or a fourth or something. This should be 4. It should be much steeper if they were reciprocals. So it's a way to try to point out to the students not to make that pitfall and try to look at any given point that they have for the derivative of one function, that they're just going to take its reciprocal and they'll get the derivative of the inverse function. Sometimes it's done in, and maybe I should have pulled some of these up, they'll give you a table. Well, they'll include the function f and then the function g evaluated at points, and then they give you the derivatives of f and g at a couple of points. And you need to make sure you use that table appropriately to find those slopes of the inverse functions. Tom, you have anything to add?
No, not on the slope fields.
Okay. Do you have anything to add anywhere?
Well, yeah, I could do
all right, then.
A few more things if you like. Okay.
I'll be glad to hand the ball over to you.
Okay.
Don't know if there were any questions out there that anybody was asking. Maybe Mike, you might have one or something. but this is my chance to show that I can hand the ball off.
Okay.
And
hey, Dan, while you're giving Tom control,
uh-huh.
we did have a question from Pauline. She wanted to know how you did the overlay of the two graphs on the TI-Nspire.
Okay, it really wasn't using Inspire software. It came in at the last minute because I managed to get the license just yesterday afternoon. I used the Smart Notebook software. You could use any screen capture tool that allows you to change the transparency of one slide over another. So I just was pretty careful to make sure that each slide that I captured, they were identical in size, and then I laid one over the other, making the top one a little more transparent so that you could see through to the bottom one. And I would like to, Tom and I were talking about, it'd be great if I could manage to get the slope fields of one to be one color and the slope fields of the other to be a separate color, so you could see it even more clearly. And maybe that's something I'll look into and provide with you to provide for the archive.
Okay. All right, I think I've got my screen being shared now. I'll tell you what I'm going to do is I'll go back to the TI-84 platform, and I realized that another example I could have shown was actually that of a function that's not differentiable. And so let me go to the y equals and pull up, let's see, under number, absolute value, okay? So that's kind of a classic function we take a look at. I was editing here, so let me get rid of that exponent there. Okay, and I'll clear out y2. And so I'm going to do a zoom decimal of the absolute value function. And there it is. And we get that, as expected, that sharp corner there. And we talk about how if you have a function whose graph changes direction suddenly, that's going to be one of those classic examples of a point of non-differentiability. But we might think, well, especially if you use kind of unequal scalings for zooming in, you might see a phenomenon where graphs will flatten out or something like that. But I want to emphasize the zooms we're going to use are equal scaling both directions. So I'm going to zoom in on the origin on this absolute value function graph. So let me just go ahead and hit the trace. I'm going to do a zoom in. And, well, still looks like a sharp corner there. And in fact, it doesn't look like anything's changing at all. So you might be thinking, oh, I'm just flashing the same screen up again. But if we actually trace, you'll see that the increment on X is quite small. Okay, so this really is a very zoomed in picture of the absolute value function, but it didn't straighten out. And so that's more evidence, not a proof. That's the evidence that our absolute value function is not differentiable because that sharp corner persisted. So that it cuts both ways. This local linearity property really is a definitional quality about differentiable functions. The other thing I thought, this was kind of coming back to first principles. Let me go back. I'm going to go back to the very first function I was looking at before. That's sine of x. And let me do a zoom decimal for that. All right. Now, if I mentioned that if we wanted to, the definition of derivative is a limit of difference quotients. And what we've been playing on here in terms of approximation is, well, then that means you can approximate the value of a derivative by using a difference quotient with as small an interval as you can manage. Now, for data, Dan indicated how you could do that is you just take the two closest values you could to the data point that your question's about, and that's the best you can do is use the two closest data points you have. But if I was just dealing with a function like sine x, I could approximate the derivative by just calculating a difference quotient where I have a small difference in x values. So for example, suppose I did the sine of 2.1 minus the sine of 2. I'll group those together in parentheses. So that's my difference in sine values at 2.1 and 2, and divided by that by the difference in the x values, which would be just 0.1. So my claim is this value here is a rough approximation of the derivative of the sine function at 2. Okay, so you might question, well, how good of an approximation is that? Well, let me illustrate something. This was actually really very startling to me. So I'm going to go back to y equals here, and let me go up and go ahead and that closing parenthesis being gone bothers me. What I'm going to do here is for y2 is I'm actually going to enter a general difference quotient function. So what I'm going to do is enter in sine of x plus 0.1 minus the sine of x divided by 0.1. So that's just a simple difference quotient. What I'm going to do is actually do that for each value of x as I graph it. So for each value of x, I'm going to take an increment of, you can think of as your h value or your delta x of 0.1 and calculate a little difference quotient there. Now that's not really a very small value of h, but let's just see what the graphs of these two things look like. So let's go ahead and do a graph. There's our sine function, and this red graph is the graph I got by calculating that difference quotient for each value of x. And I was actually bowled over by this because to me that value of 0.1 is pretty crude. That's not really that small when you think about really zooming in on the graph. But even at that level of h value, I'm getting a graph that looks very remarkably like a cosine graph. And it really warms my heart when I do this illustration in class where students will say, hey, that looks a lot like cosine, and where they're recognizing that. So it's really quite amazing. And I don't know if you can see it, but here at 0, 1, you can kind of see that it's not perfectly symmetrical. And that's because I was doing what's called a right-hand difference quotient. So I went 0.1 above the value, and so, you know, if we had plotted, I'll tell you what, let's take a look at, let me go back to y equals, and if I'd used, fumble around here, I'm going to change that plus to a minus, and then I'm also going to need to divide by negative 0.1, because my h value is negative here. Let's graph that. And I don't know if you can detect it. It still looks really, really close, but you can see it's a little bit, not quite symmetric, but in the other direction. So, and in fact, on your calculator, an even better version of this is what's called a symmetric difference quotient. And what that would use is, instead of sine of, let's see, illustrate what that looks like. So I'm going to use a sine of x plus 0.1, and instead of x, I'm going to actually put in x minus 0.1. And the difference in those two x values, let's see, is actually now 0.2. So I'll divide by 0.2. So I'm taking the sine of x plus 0.1 minus the sine of x minus 0.1 and dividing by 0.2, the difference in the two x values. Let's graph that. And this thing is remarkably symmetric. In fact, just for grins, why don't we go back to y equals and graph the actual cosine function. And oh my gosh, you can barely, it's such a nice, there's just a few spots where you can see a little patch of red. You might not even be able to see it on your own screen, but I can see just a very bit. So that symmetric difference quotient, even with an h plus or minus h of 0.1, so you're dividing by 2h, is a remarkably good approximation for the derivative. And you can actually plot it. So like I said, I was really bowled over by how good a job that difference quotient can do in approximating the derivative of a function. In fact, this is what underlies on the calculator the derivative function. If you don't have a computer algebra system calculator like a TI-Nspire CAS or a TI-89, the derivative functionality on the calculator is actually a symmetric difference quotient for a very small value of h. So when you go to your math menu on the home screen and you see nderiv down here as number 8, and here on the, we've got this nice format of notation here. So I'm taking the derivative with respect to x, and I'll go ahead and pick up y1 which was my sine function. And if I was going to look at the derivative of that at, say, x equals 0, it would do a symmetric difference quotient for a small value of h. And here we're getting 0.999. It's looking very, very, very close to 1. And remember, that's the very first thing we looked at in the webinar tonight, was we zoomed in on the graph of y equals sine x at x equals 0. And it looked very much like y equal x, which has a slope of 1. So that was a little foray into kind of what's going on in terms of approximations for derivatives. And it's just really coming back to this first principles that if our graph behaves like a straight line up close, then just doing a simple slope calculation for two points that are very close is going to give us a good idea of the derivative value at that point.
Hey Tom.
Yes.
Dan here.
Yep.
Could you kind of make reference to how this symmetric difference quotient can be fooled by something like absolute value, where it yeah, you see where I'm going, you see where I'm headed with that?
Sure, yeah. In fact, let me give this a shot in this way. I'm going to go to y equals, and I'll just go ahead and change my sine function over to absolute value. And let me get rid of the extraneous stuff here. So now y1 is equal to the absolute value of x. And now let me go back to the calculator screen, and let's recalculate the derivative of y1. Now remember, y1's been changed now to absolute value. And let's see what we get here. It's actually reporting 0. And we know that the absolute value function is not differentiable at x equals 0.
Excellent.
Yeah, and we can explain that as the fact is what has happened here is this has actually calculated a difference quotient, not the actual derivative. So it took a value on either side. So if you think of the absolute value of 0.1 minus the absolute value of negative 0.1,
can you go to the graph again?
0.2,
Look at your absolute value graph. Can you go back to your absolute value graph?
Sure. And let me turn off these other two because that will get in the, that'll
If
distract.
I may, that is a very important concept of the difference between the symmetric difference quotient and the actual definition of the derivative. And this other idea that for differentiability, you have to have the limit from the left has to equal the limit from the right. The limit has to exist at the point. But with the absolute value function, your left-hand and right-hand limits are not the same. Even without calculating it, the student should be able to see one is negative from the left, the other positive from the right. They are not the same. But if you do a symmetric difference quotient, you get this wonderful horizontal line at x equals 0.
Yep.
And that gives you a slope of 0. So it's a good part about pointing out to students why it's important to know the definitions of things, because technology often uses, what's going on in the background. When it says it's the derivative, is it really the derivative or is it the approximation of the derivative?
Yep. And I just realized, another way to think of this symmetric difference quotient is when we did the cosine, it was kind of when I did a one-sided difference quotient, it wasn't perfectly symmetrical. And so the right-hand difference quotient was skewed a little bit to the left, and the right-hand one, or left-hand one was skewed a little bit to the right. What the symmetric difference quotient does is it averages those two. And you can see on the absolute value function, if I average the slope to the right of 0, which is positive 1, with the slope to the left of 0, I'm going to get 0. And that's how it's been fooled, because it's doing a simple average and not really detecting that there's a problem of differentiability there. So yeah, very good point. Yeah, approximations of derivatives will not work very well if you're at a point of non-differentiability.
And so if I may, I've noticed some of the comments out there. We got some people that are new to teaching calculus, and my thing I'd like to say to them is hang in there. Don't over-expect for the first year. There's a lot to learn. But I think, I'm not sure if it was something that I was at, that you were at, Tom, where people were sharing the statistics, if it was not last year, but the year before at TQ'd with the conference within a conference. But they were looking at student success rates in Calc 1 for students who had taken AP Calc in high school but had not passed the AP exam. It was still substantially greater than students who had not taken AP Calc at all. And that's an important statistic, and I tell that to many of my students, some who really don't feel that they've got a good enough command of AP Calc. I get varying levels of ability because I don't control the pre-calc that's coming into me, but it's still a worthwhile thing to do and to hang in there, because many of them do go on and do quite well.
Yeah, and that experience of being in a challenging course, it pays off dividends, even if they go on to retake Calc 1 and at the college level.
Exactly.
That experience in a really good AP Calc course is invaluable.
And getting back to the absolute value function, folks, I actually do have a couple of screens here. Could you hand the ball back to me just briefly before we send it over to Mike?
Sure. Here we go.
Because as you were talking about that, I went off and let's see here. Where's it's back to me. So there it is. Okay, share my screen. Okay. So the one course that I'm known to have dropped in college was Advanced Calculus for the Sciences, and I dropped it on the very day that they said, today we are going to prove there is a function that is continuous everywhere yet differentiable nowhere. And what is that wonderful function? Well, here is the graphic representation of it, where they zoom in on the local linearity down here. And it is essentially so jagged everywhere, if you were to zoom in, would always be a corner point. Kind of hard to imagine. But they have a very nice, let's see, where was it? There's a video here. Where did my video go? There it is. Okay. This video shows what happens. Look at that animation. This nice smooth curve starts to turn into this jagged edge. And you can see how it goes to being differentiable nowhere. So I just kind of wanted to share that. I even bring it up with my students, though it did drive me out of advanced calculus for the sciences when I said to myself, when am I ever going to use that? I did actually go back later and take partial differential equations a year after taking differential equations, which I let my students know is never a good idea, because then your professor says, and now the rest of it is a simple ODE, and you're running home going, oh my God, how did I solve that again? So please take your partial differential equations immediately after your differential equations. That's my advice.
Well, it was interesting how they illustrated with a little magnifying glass, in a sense, that they were zooming in on this jagged function, and that was kind of illustrating that even if you zoom in, you'll see it continues to be jagged.
Right.
Yeah.
Exactly. That's that local linearity made me think of that. So
it's failing to be locally linear in
right.
a spectacular way. So, all right, I think that probably does it for us. So, Dan,
I'm going to
pass it back over to Mike.
And I'm going to send it on over to Mike. And there we go.
Thanks so much, guys. As we begin wrapping things up tonight, there are a couple things I do want to share. Some resources on our website, education.ti.com. Whenever you visit our website, in the middle of our page under resources, check out the tutorials. I think Robert had already mentioned this earlier. Oh, nope. How about professional development and webinars? So Robert, thanks for the free plug. So Robert, I think I mentioned the on-demand webinars, which is a great place where you can view all of our previously recorded webinars that we did. But I do want to highlight some of our upcoming webinars. Right now you're obviously listening to and watching Calculus Getting It Straight. But if we scroll down to October 16th, there's another Calculus-specific webinar coming up, and another one on December 4th. So if you haven't registered for those yet, those may interest you. Feel free to visit our website and register for any that you may be interested in. Also, I wanted to mention under the Resources tab are the TI in Focus, and they're specific to AP Calculus. Even though they're specific to AP Calc, they still talk good calculus. So I've used these with my students. I started using them last year. Tom Dick and Steve Kokoska, I believe, are the two gentlemen responsible for putting these together, and they're going to grow year by year as we acquire more AP exams. The differential equations, kind of interesting that we started talking about that tonight. I'd used my students last year, and the thing I love about what Tom and Steve put together is you can begin to see some of the resources that are available for some of these really, really challenging topics. So please feel free to visit our website, register for some of those upcoming webinars, watch some of the on-demand webinars, and check out some of those AP Calculus resources on TI in Focus. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents that were used tonight by Dan and Tom. And if these aren't working for you for any reason, just hang tight. In a couple of days, you'll automatically receive a follow-up email. And in that follow-up email will be a link to the recording, a link to the certificate, and a link to the documents. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Thanks so much, Dan and Tom, for everything you shared tonight. It was fun.
All right. Thank you.
Thank you, Mike. Appreciate it.
And thanks again to everyone for joining us, and we hope to see you back online real soon. Have a great night.